I am the co-founder and president of the AUROS Group. Our business is focusing on the intersection of building science and data science. We're deeply into building efficiencies, and we use a lot of different technologies to drive to building efficiencies. Most of them are in the building energy model world. And then we take that modeling data and we're able to ingest it into the data science world. And we're going to show you guys today what that kind of looks like. The idea here is that up until this tool, the building science community never really had a voice in the data game when buildings go operational. And we want to change that, right? The building science community is responsible for making those decisions on how the building is supposed to get set up, operate, and we want to make sure that they have a voice in operations. So we developed a product. It's called AUROS Insights. What is AUROS Insights? So AUROS Insights takes building energy modeling tools, and those tools can be the dynamic tools of eQuest Energy Plus or ISVE. It could be the block tools that are passive house compliance tools of PHPP or WFI Passive. And it could also be subcomponent modeling tools. If you're doing subcomponent modeling, these can also be used in this environment. It also uses a technology for IES's product ICD, which is a community development product where we can model a group of buildings all at one time. And the idea is that how do we take all of those great tools that exist for the design community today and operationalize them? And that's what we're going to show you today. So to do that, we have to talk about these disparate data sources, right? So there are meters that go into buildings. We need those meters to calibrate our models. There are HVAC equipment and building automation systems that are in buildings. We need to get the data from those buildings, again, to calibrate our models. And then simulation comes into play. Once we have a calibrated model, we want to be able to bring that data back to the same space that we just took the data from. We're talking about time series data here. And if we can do that, then we've just basically integrated those data, the time series data points. That's the first step. The second step is now that we've made that integration, how do we normalize it? How do we get the data on the same unit of measures and the same key performance indicators so that when we're looking at it, we understand what the building should be doing? And that's what we're going to talk about today. And we're going to show you how do we ingest the data, how do we normalize the data, and then make it available for different things we want to do with it. And those are the use cases. And we have two use cases that we developed so far. And I want to be able to demonstrate each of those use cases today. So again, if you have any questions along the way, please raise your hand. I'm going to show you and demo, pop out of the PowerPoint here at about 3 different times and be able to show you these tools as well. So let's get started. This is chaos. So what we're showing you here is we're showing you an example of a smart building infrastructure deployment in a typical building. Now, you may not understand all the technology that goes into this, but we certainly understand that we have building automation systems in buildings, right? We certainly understand we have lighting control systems in buildings. We have access control systems, security, CCTV. We have utility meters. There's probably about 25 different operational technologies that exist in buildings. And this is an example of how that data is organized. Someone who practices in this space like we do, we understand this. But for the building science practitioner, they don't. And when the question comes to them, how do we start taking the data that we have and ingesting it? When we don't understand how to do that as a building science community, then we end up doing it in a disparate silo, right? Then we basically take our data into our own Power BI, our own Excel sheets, and we do all of our work there. And we're working with the data from these systems offline in a CSV format. We don't want to do that. We want to work in a real-time environment. But data has to go home, and data home for data is at the data layer. So instead of looking at chaos like this in terms of how buildings are managed, we prefer to look at it like this because it's a lot easier. There are 5 major systems for smart building infrastructure in a building. And they're pretty straightforward and simple. We don't have to look at the chaos on how the sausage is made. We only have to know that the operational technologies exist. And the data that flows from these operational technologies typically is going to flow through what we would refer to as a converged network into a data aggregation point. This point can be hardware or software. And this is going to be where we translate all the different protocols of data across these operational technologies into a single language, English, so we understand it. And all the data then can be housed and a historian. This historian gives us a single pipe connection into the building. So from the building science community's perspective, where do we bring physics-based simulation into it? Because we are classifying physics-based simulation, a building energy model, as an operational technology. Building simulation is not an on-prem meter or sensor, but we generate a lot of data. So we're an OT, right? How do we get in the game? We get in the game right here at the independent data layer. This is where it happens. And we have to be agnostic to be able to come into the different data layers that exist today. And there are probably about 5 or 10 data layers that really are common in the market in the built environment. All 5 to 10 of those data layers have AUROS Insights in them. So you can literally bring this data and meet the client where they're at in their data world. And then when we do that, then special things can happen and we can start talking about the use cases. All these capabilities over here, people get confused and they see a digital twin and they see the digital twin and they think the digital twin is going to have a connection to every single operational technology in the building. That is not best practices. It's not what we do in the smart building infrastructure space. Because again, when we want to pivot from that digital twin to another digital twin, it becomes very difficult to extract them from a building. But if that digital twin connects into an IDL or an independent data layer, then it's a single pipe connection. Cut them, bring in the next twin, plug it in just like you would an app on an iPhone. Now all of a sudden we're in the game. That's why data has to reside at the independent data layer. And then all of the technologies over here become available for simulation to also play a part in. Because what's happening over here, guys, in this space for data analytics and building optimization is those tools have been using history and comps forever because that's the only data they have. But history and comps don't answer the fundamental questions. Did I get what I paid for? And is the building performing in the way in which it should? When we use simulation in lieu of history and comps as better context on the building data, then these use cases really emerge. And that's what we're going to talk about today. All right. So the first thing we want to talk about is this independent data layer. This one I'm showing you on the screen is Novant, and I'll demo Novant. So just to go back to here, this is the data layer. There are many data layers. You can go into a Pi system, OSI Software Viva Pi. You can go into Novant. You can go into LinkSpring. You can go into a lot of different. And there's Atrius is coming out right now. Tandem has one. Autodesk. These are the data layers that exist. And what I'm going to show you is I'm going to show you an example of one. If you see one, pretty much seeing them all. They're doing about the same work. So what I want to do here is I'm going to pop out of the presentation and I'm going to show you an example of what an independent data layer looks like. All right, so this is Novant, and if I go into a specific building here, just to give you a lay of the land, we're not going to go too deep here, but I just want to show you what a data layer looks like, right? Is that it's managed into these different types of modules, and this is where the data sort of resides. So if we go into spaces for a specific building, you'll notice that we have all the room numbers by all the floors, and we have the actual building. And this is where we start to create relationships. This is extremely important, and this needs to be done at the data layer. Because when the capability layers connect to the data layer, all these relationships can be given when we give data. And it makes the time for setting up those capability layers much, much less, right? We can go way faster. So what you're seeing here is this is how we start to build relationships with spaces. And then we go into assets and we start building these assets out. Assets can be a piece of equipment, this air handling unit, the air rotation unit. This could have as many as, if I click on it, it could have 50 points in here. These points are just data points. These are the time series points. So if I go in and I give you one here for air supply temperature, and I look at this trend right here, this is what a point is. And if you want to see it as a table instead of a chart, every hour, the way we're setting it up for sampling, is we're getting a independent, unique point. That's what time series data is. And that's going to give us a trend like this. So what we want to be able to do is we want to be able to manage them again in the assets with the right data ontology, the data attributes here, so that as we connect in those capability layers, we're able to give it. This particular project here I'm showing you is a Reset Air certified project. And you'll notice here, these are my Reset Air monitors, amongst others. All the metadata here, which is our static data, is what we're using to connect to Reset Air in the background. So this data layer can literally connect that to other capability layers like that too. And then if we go into sources, this is where we manage those points. So if we come in here, and I'm going to show you a monitor because it's kind of the easiest thing to see here, right? So this area, BGM North, this is a location for an indoor air quality monitor. This monitor is a 6-parameter monitor managing temperature, humidity, CO2, PM2.5, and PM10. It's a reset air monitor. And again, when you see the values like this, you'll know that this is a point, meaning if I want to see what my PM 2.5 is, and I trend that guy right here, it's a point, right? The idea here is we can bring simulation into this environment. And we've set up all of these structures here to make it easy for you in AUROS Insights. So when you connect, you simply drop your data. So under the simulation for operational optimum steps, I'm going to show you these. These are different models. We have to give our models names, so we model from them. And when you go into here, you'll notice that this is the BTUs coming out of the model right there. That's what's coming directly from the model into the data layer. These are points. And then we convert these points using AUROS Insights data analytics into all of our usable points. And I'll show you this in the use case too. So if you want to see these trends real quick, just because you want to trust me, there they are. And we're looking at a unique point for operational and optimum. I did not have steam, hot water, or chilled water, so those are going to be nulls. Yeah, it's just electric and gas. Those are the only 2 utilities we have on this project. So that in a nutshell is what an independent data layer is. It does a lot more than just this, but those are the basics. If there's no questions, I'm going to go back to the presentation here in a sec. All right, that is what an independent data layer is, and that's where the simulation gets integrated. And then we need to talk about, once it's integrating the building energy model, how do I make the data usable? How do I make the data actionable? We have to normalize the data. What does that mean? For simulation, right? For electrical simulation, we're going to be, sorry, I just clicked twice. We're going to be exporting a BTU. That's what it is in a model. That's how it works. So if we do our simulation, we're going to be able to have a 1-hour interval BTU for electric and for gas. These are our source UOMs. And then we want to convert these to usable unit of measures. So what we're doing is we're taking that BTU and we're converting it to kWh, which is your electrical unit, so we can match it up against the meter. And then we're going to convert it, what's already in BTUs, we're going to convert it to dollars, and we're going to convert it to location-based carbon emissions. We use 2 methodologies which are consistent with the greenhouse gas protocols. One is the eGrid right here, which is the annual blended rate for your emission factor. But the greenhouse gas emission protocols say you want to be location-based and you want to use a fidelity of 1-hour interval if we have it, which is EIA. EIA balancing authority data is in 1-hour intervals. So we're calculating this across 2 different methodologies. And we do that because our clients want to make sure that they manage a transition, right? Historically, they're doing this in spreadsheets. They're looking at annual data for consumption, and they're pretty much using Energy Star Portfolio Manager metrics to do that. So eGrid is going to line that up so that they can say, yes, this is working. This is what I expected to see. And then we're going to move them into an hourly factor because it's more efficient. It's more right. And we can get the time of use studies, which we're going to talk about in a second. And once we get it to the unit of measures here, we also want to go into our key performance indicators, which is site EUI, source, cost, and carbon. Same thing, only these are rolling 12s, and these are all calculated in 1-hour intervals. We do that across all utilities. And then we combine our KPIs, so gas, electric, any other utility coming in the building are all combined to give us a combined KPI here. Meters are about the same. The challenge here becomes your electric meter as a watt hour is a totalization meter. And that's the way all meters work in buildings, right? They're going to basically say, we're at 100. In hour 2, it's 102. Hour 3 is 104. And it just looks like a line that accumulates. So we need to convert that from an accumulation meter to a 1-hour interval. And then we need to convert it to the same unit of measures I just described for simulation. Now we can compare meters against sim. We do this for invoice data. We can do this for any kind of statistical regression if clients are using that as their forecasting tool. Again, we want to get it into the 1-hour interval and then work in the unit of measures that makes sense for us. And you're going to see an example of why this is so important when we go to the user interface. So what we want to talk about here is we want to get into these two use cases I mentioned earlier to the group. We're going to talk to you guys about two different use cases and why this is important when simulation is put in the same environment. The first use case is operationalizing the model, and the second use case is going to be scenario planning or creating this energy efficiency and decarbonization tool. I grayed this out because we're going to talk about this use case in a few slides from now, and we're going to be focusing our efforts right here in this operationalizing the model. This is the most obvious use case you can imagine, right? This is an example of it right here. I have a KWH. I'm looking at a dashboard. How many people have looked at a dashboard and saw a KWH and they're like, is that good, bad, or indifferent? I have no idea what that means. I see a line, but I don't know what that line means. We need to give it context. And the digital twin environment or the data science community has been using history and comps forever. So they're going to tell you at first, without having simulation, well, you're better than where you were yesterday, or you're better than you were the average of the last 3 weeks, right? Again, those aren't answering the questions. If I want to invest into building performance, then it's going to change. History doesn't know what a double pane versus a triple pane window looks like. It doesn't know what, 5 more inches of insulation in my roof's going to do for me. It doesn't know those answers. And it doesn't answer the question, is the building doing what it should? So monitoring-based commission is the most obvious use case in operationalization of the model. Then we have interrogation-based commissioning. I guarantee you it's far cheaper for a building scientist like you guys to go into your model and start saying, did you change your set points? Is the building turning on later than it should or earlier than it should? Did I change my lags and leads? We can start interrogating the building very, very quickly and identify where those gaps are without doing retro commissioning, which may cost hundreds of thousands of dollars with boots on the ground, people blindly walking through a building. Why not start with our technology first, see if we can locate those gaps and fix the problem? And then there's this emerging use case here, and this is fault detection and diagnostics and automated functionality testing. I'm going to talk about these in a minute here. So this is fault detection and diagnostics. I'm not going to give you guys a visual today on this because it's sort of like a click deeper than we're prepared to do today. But I have a presentation. It's on my website right here. You can go and look at it if you have an interest in this. But what FDD is, guys, is FDD is setting up rules. It's looking at the meter and sensor data for equipment, and it's asking questions. Am I heating and cooling at the same time? We can see that through the trends of the meters and sensors on these equipment. Is a damper open and it should be closed? Is my ARU off and the system's calling it to turn on? It's a fault, right? So it's a very binary this or that program that we can set up rules to start interrogating buildings. But what this limits you is it limits you in looking at things as a trend. Because if it wants to set up and say, hey, look, I want to know if my ppm for CO2 goes over, 800 ppm anytime, give me a fault. Well, what if no one's in the building? Do I care? Right? So the question becomes is we want to start looking at this dynamically and not statically. So what we do is we set up the trends, and you'll see that we have it set up for indoor air quality and and utility consumption here. And we want to understand when the sim gaps from the trend. And when it does, I want to spark. I want to know because something's happening. So this is a different and unique way of using fault detection and diagnostic, a tool that's been used and proven in the industry for years now, and using simulation in this space. And it's extremely powerful. Again, if you're interested in this, go to this website and you can look at that video. I would also suggest the automated functionality testing. When you think about that, like buildings have been doing commissioning forever. We get to the punch list and here comes the commissioning agent. And now these guys are walking through the building and doing all of their work. We argue that we can set up automated functionality testing to alleviate a lot of the burden of manual people walking through our buildings. Why not use technology and basically limit what I have to do in functionality testing? That's taking place right now, and it's an extremely great tool. But we're looking at that and saying, why not use SIM? If I've got the whole sequence of operations and set points in my model, can I not export that into a data layer and use that for automated functionality testing? And the answer is yes, we can. And we are doing it right now. So now all of a sudden we've taken a tool that's emerging here in the industry, this automated functionality testing, and we ingested simulation into it. And it's really changing the way that works, which is pretty cool. So that is another example of operation in the model. And what I want to do is I'm going to pop out one more time here, guys. I'm going to show you a couple use cases on operationalizing the model. So this is a simple user interface. And user interfaces are always the easiest thing to solve. If you've got the data in the data layer and the data is normalized, setting up these user interfaces is super simple. There's 1,000 tools that'll do this. But what you're looking at here is we want to start to use simulation a little differently. So what we're looking at here is now meters, invoices, and simulation. This is an automated calculation, site, source, cost, carbon, and water use intensity. This is happening in the data layer in real time. We don't have to touch it. We don't have to maintenance it. It's giving me my rolling KPIs for all sources of energy that come into the building. We're basically automating scope 1 and scope 2 right here. We never have to do this in a spreadsheet again. We can look at it as a trend because it's all hourly. All this data that's in here right now is all hourly data. So if I go into here and I look at site EUI and I can toggle through my site source cost carbon, we can see this hourly for all of these metrics. But it gets really cool when we look at utilities. So now we're looking at the electric feed. This is primary source electric, guys. This isn't a sub-meter. We can do it for sub-meters, but this is primary source. So we go into here, and what we're looking at is electric. We have gas and water. I'll show you gas in a sec. And it's at a kWh. Because we normalize the data across all the KPIs, I can look at it as a cost. I can look at it as carbon for eGrid, and I can look at it as carbon for balancing authority. The blue line's the meter, 156,000 kWh in the month of January of 2025. The simulation says we should use 164. It's pretty good. We can drill down. We can look at it over a period of a day, or we can look at it. Let's go back to day, and let's go back and show you hours. That's hours. Now you can start to see where fault detection and diagnostic plays a role, right? I got a gap. I want to know when that gap hits, but if I'm pretty much within a percentage of a delta, then I'm good. This is where FDD comes into play. So now we can start looking at this. And when you think about it from a sub-meter perspective, there's a lot of volatility that gets removed from the system. It becomes that much more powerful. If we click out of this, and we're back up at this level, we can flip it over to costs. Now, the same exact thing, we're seeing a dynamic version of the cost on this. There's how much we spent, $17,200 that month of September, and we can drill in. And all the metrics are flipping because the AUROS Analytics does it for all forms. And we can go in there and look at this hourly now. And what you're seeing is we spent $5. This goes to time of use. When we start talking about time of use, when is the energy generated? When is the energy used? We want to do that at the optimum times a day for both carbon and costs. And then we can do the same thing for carbon. If I click over to here, it's just going to flip to pounds, and it's going to give it to you for that type of use. Gas is no different. We go to gas and pop out of here, and you're looking at it for the last year. And this is the curve we expect to see. We don't use gas in summer times. We use it in the winter times. But again, this is working the same exact way. Now, gas does not have the EIA because there's no EIA factor for gas. It's a fossil fuel. It's always going to be EPA. But again, we're looking at this and we're able to see this in any unit of measure we want to see it in. It's really, really powerful for reporting too. So this is not just used for utilities, although I'm showing you a lot of use cases for that. We can also do it for IAQ. So now we have a building that has 9 monitor locations that are 6 parameter monitors. Coming across the top is now with context. This is the parameters. And this, while this graph looks busy, my client likes to look at it this way because they're looking for these outliers, right? Because this building is a really high performance building, and we have the static thresholds we could turn on right here. So there's reset for 600 ppm and 1000 ppm. So this building you can see on the normal days is performing really, really well. But if we want to see like what's going on here, something happened, right? At 1222, at 1600, this spiked to 2100 ppm. So either a fan's not working or they had an unexpected event and they didn't schedule it accordingly because the sim's way down here and we want to understand the differences. That's why we kind of set it up. But you can view this any way you want. And we can do the same thing for temperature and humidity because we can simulate for those as well. And now you can start to see what the expected simulation is versus what the actual performance was. And we could do it for humidity. So this is giving you an example of how you would look at monitoring-based commissioning, how you can drop in interrogation-based commissioning. And then I did not show you fault detection and diagnostics, but you guys have the video on how to do that. and I'm going to show you guys the next use case. So this use case here is scenario planning. So think of a model or building, right? So if I go into an existing building and I create my first model, I want to make sure my model is validated, that the work I'm doing with the model is working from a calibration point so that any deltas from that are going to be actual. So the first model we create is called the operational model. We calibrate it back to the building, and we can calibrate our models to under 1% of the building using the ASHRAE 14 guidelines. Then we want to create scenarios. So maybe the first scenario is you're like, what if I went in there and I did a passive asset retrofit for that? Well, we model that and we call that the optimum model. Now you see the edges of the spectrum, right? You're here, and the best building you could build based on building science pre-renewables is passive ash. You're here. And then we usually end up somewhere in the middle. So in here, you're doing one of two things. Either you're looking at optionality. In other words, I got a major or new construction or a major retrofit, and I'm only spending my money one time. So you're going to look at the edges of performance, and then you're going to model run optionality on the optimum model because maybe cost constraints, maybe constructability, and you're going to figure out what the best building I can build is. So this could be used as optionality. We're going to find the best building for the budget. Or this can be used as a phased execution plan. Maybe we have an existing building and we want to respect our triggers. What are triggers in a building? They are going to be life cycle, deferred maintenance, plan renovations, and we want to utilize the money that we're going to spend in the smartest way possible. So we're going to do a phased execution plan. We know where we want to go, and it's going to take us maybe a few years to get there. So in year one, we're going to do our roof. In year two, I might do a renovation of a space and I start replacing systems. And I can start looking at the whole deferred maintenance schedule and model those over time to figure out how do I get to this level of performance. Instead of replacing in kind or incrementalism, we can start to create a phased execution plan. That's what this is all about right here. And what we're going to do is we're going to show you, we did this using IES's ICD product. And I'm going to show you how we modeled 12 buildings on George Mason University's campus. And we dropped it into a data layer. And then we able to use that data to start giving us the information that we want to see so we can make these plans. Well, I'm going to show you this first because I showed you the chaos for smart building infrastructure first. So I'm going to show you chaos in a building science world, right? Well, this is chaos. Is what you're seeing here is we only did two models for the Delta. We did the optimum model and the operational model, which is OP and OT. So now we can create a spreadsheet, right? We could put the 12 buildings up on the spreadsheet with these key KPIs across the top, and we can look at site, source, cost, and carbon, and we can start seeing our deltas. It's very hard to read. It's not intuitive. It sucks to set up. It takes a lot of time. And we have to make all these conversions manually, right? This is what we've been doing for years and years and years. There's an easier way. And the easier way is to going into an independent data layer like this. And this is going to be our next use case I want to show you guys. So I'm going to pop out of here. And I'm first going to go into Novant because I want to go back and show you from a project perspective. Here's George Mason University. And again, I'm now back in this independent data layer where we manage all the data. Okay. So we go into spaces. These are our 12 buildings from here to here with, actually, I should hold shift on. Okay. These are our 12 buildings. This is our campus, and we set this up too because we have other metadata we want to associate it with. And then from this, we can get into the assets, which in this case are set up in a group here. We have baseline data. We have the simulation. I didn't show you calibration analytics, but we've automated all the calibration analytics here for these. So any modeler in ASHRAE 14 is going to understand this. We've automated all this. This is done hourly. But I'm not going to spend a lot of time here today on that. I just want to show you that's automated, but there's our simulation for the optimum and the operations, and there's the whole building metrics. And we did this for 12 buildings. So it starts here. That's building 1, 2, 3, 4, all the way through 12. And then our sources are over here. And these are the points. So now you can see under the operational model right here, this is where the model is going to kick out the BTUs. The model kicks it out through an API, plugs it directly into Novant, and then we run the analytics to convert our units of measure and our KPIs for everything else. This is how straightforward it is. And we can do this because it can templatize the independent data layer, we can do this for as many as you want. I can do operational optimum. I can create 15 step models if you want to do that. But now you're starting to see how this all starts to come together rather than us doing it in Power BI or in Excel. And when we do that, we can create an interface. This is an Excel-based interface. It can be used in Power BI, and this is how we start to manage campuses. So I'm going to show this to you kind of at this level first. I know it's hard to read, and then I'm going to drill in. So just hang with me for a sec. So this first screen up here is a specific building. It's Amherst. I could change all my buildings. And when they change in this chart. They change on the district energy plant, and they change on the KPIs for the East Energy Conservations. This is the campus. So you're looking at the entire impact. So how do I know what that looks like? So there is the building. And what this is from now till 2050, because we want to do a life cycle analysis cost of this is business as usual, right? We've got our history, which is our invoices, that's our baseline data. And then we model and simulate out here. The costs are going to go up, and they're going to go up at these rate increases, which are EIA rate increases. If we disagree with this model gives you the chance to change it. So maybe you look at 3.5%, it's too conservative. We think it's going to be 5%. Change it, all the numbers change. All the numbers change everywhere, which is really cool because now they can start to manage this. We can do it for gas in the same exact way and change gas to 10%. This over here is just a stack of the utility: electric, district hot water, and chill water. There's no natural gas in these buildings. These 12 buildings we modeled because they're all on their district energy loop. That's why we picked them. So you have the two off the district energy loop, and then you got electric coming in. This is the portion of energy that these buildings are using, the deltas. Over here, this becomes where we want to look at these changes. So we already modeled the operational model and the optimum model, and I'm going to show this to you in a second, but I just want to show you how this would change for Brunswick, for example. If I say that we're going to implement the optimum model in 2030, the building changes. We could put as many simulations into here as you want. So this is where you could start to see, like, the data layer doesn't care. I can manage 10 lines in here. So maybe we do this phased over a period of years and we start showing the value. The calculations between the lines and all the life cycle is done automatically behind the scenes. It's also done for the campus simultaneously. So I'm going to pop out of here for a second, just so I can show you some other ways we created uses here. So we know Fenwick is the highest consumer of energy, and we know David King is the second highest consumer of energy. We know that. It's pretty obvious. So if we go to Fenwick and say, listen, we just want to make life easy. What if we just did Fenwick first? When we went in there and we said Fenwick's going to be a 2030. So you're seeing the delta on Fenwick right here. And we'll go back to those 2.5 and 2.5. I think it's 3.5, but whatever. So now you're starting to see this, and you can see that Fenwick is going to significantly impact the campus's numbers and the district energy numbers. So as we select our buildings here, we can change our electric here. You might say, like, we don't care about cost. Maybe we care about carbon. We don't care. There it is. There's total energy here. There's site, source, cost, and carbon. If you want to look at carbon, there's carbon. Now, carbon will basically have a profile like this. Why? Because the grid, based on the building performance standards for this area and location, is going to decarbonize. They're going to substitute fossil fuels and put in more renewable energy, and that grid is eventually going to decarbonize, but we can't wait for that. So this is it right here. And they say that they're going to decarbonize by 95% by 2050. Maybe our clients are skeptical. Maybe we don't think they're going to do that much. We can change those numbers and manage that risk ourselves. And if you want to look at this for electric, hot water, chill water, or combined, because we're looking at combined right now, maybe you just want to see electric. There's electric for everything, because we already did the math, right? In the data layer, we did these calculations across individual utilities and a combined utility. So now we can go in there and we can see the total impact. So when leadership at George Mason or any of these campuses makes a statement or puts out their policy and says, we want to be 50% decarbonized by 2030, and we want to be 100% carbon free by 2040. And then facility managers throw their hands in the air and are like, we don't have a clue how we're going to do that. We don't have the first foggiest clue how we're going to get there. Maybe we should just go buy a really, really big PV array. We could start going to these guys and do scenario planning. Leadership can use a tool like this to do scenario planning, and they can figure out, how do I use efficiency first, renewable second, as a best practice to start figuring out how I'm going to meet the goals that we've just established. So now those goals aren't pie in the sky anymore. They're built on empirical data. And we can do it for district energy because these guys have a district energy facility. It's at lifecycle, and they're talking about replacing it. And we're looking at them and saying, you haven't even talked about efficiency at your buildings yet. Don't you want to kind of do that first and make a smaller plant? Spend less money on your plant instead of spending all your, $1 billion on your plant and then never having an efficiency conversation for your buildings. And as you can see here, we can look at the plant. We don't have the plant modeled, although AUROS Insights can model a plant, and we're talking to them about it. But we can see the impacts on it because we understand the demand. If the demand on the plant for hot water and chilled water for Fairfax County are these numbers right here, as we switch our buildings up and look at these deltas, this is going to be your life cycle right here, and this changes. So what you'll see, if I change this from Fenwick to David King, then you'll see this totally changes here as well. So we can see how we can start to take the burden off of our district energy facility and use efficiency as a metric now. And when you want to have a district energy plant conversation, we can have that. And we're still looking at carbon over here, but we can change that KPI to anything you want. So again, this is just another way to start using a program like IES's ICD program. We can model 12 buildings at the same time. We can run 2 different scenarios for operational and optimum and even steps. We can drop that data into data layer, and then we can start using it for these kind of planning purposes. All right. So then, in conclusion, what we're talking about here is we want to first integrate our data, then we want to normalize our data, and then the building science community has gotten in the data science game. And then we can start asking questions. Did I get what I paid for? What's the optimum performance of the building? Efficiency can be evaluated, and we can look at empirical data for efficiency without saying we can't afford that. And this didn't take a lot to do. To do the ICD model, it literally took us about a week and a half to 2 weeks to stand that model up for those 12 buildings. And then once the model was stood up, the integration with AUROS Insights happened within hours. And then we have the model in the data layer. It's all normalized, and we can start bringing it into the user interface. The user interfaces I demonstrated for you, in addition to other user interfaces like in Grafana or Power BI, would come with the AUROS Insights tool. So you just give us a call and we'll talk to you about it. AUROS
Craig,
Insights,
sorry,
yes.
I just wanted to say Dan in the chat has a question actually.
Yeah, Dan, please come off mic.
Well, I think you answered it with this screen. This 33,600 per building per year is the license for using the AUROS program.
Correct. So we have patents on the integration of simulation and the work that we just demonstrated for you. So what we do is we would license that to you for $3,600 per building per year, and would come with the integration, normalization, and the user interfaces.
So if you were doing a campus, it'd be 3,600 per building on the campus.
Well, Dan, I would say call us. There's an economies of scale, obviously, that's going to be in play here. We are doing this work at Stanford, and we're doing this work at George Mason University. And for them, Stanford, we modeled 600 buildings at one time in Stanford and brought them into an IDL for them. So when you have an economies of scale like that, call us. This is really kind of giving you a one-off view. If you had a building and you wanted to come in here and basically see how you guys can automate the integration and normalization and automate your scope 1 and scope 2, then it's $3,600 per building per year.
And AUROS has written this program in some language. I assume it's not just an Excel template.
Oh, that's the beauty of this. So let me go back to this, because that's a great question. When we started doing this work about 7, 8 years ago, Dan, we figured, oh, let's go to the biggest technologies in the building because that would make the most sense to do our integration. So we called the JCIs of the world and the automated logics of the world, and they just simply weren't interested. This is outside their wheelhouse. They didn't get it. They didn't want to get it. They were making too much money doing what they're doing. They're just never gonna understand the innovation. And then we said, okay, let's go over here to the digital twin side of this, and we started integrating with them, and we've had success doing that with the digital twins. So our technology is in their space. But what we figured out is I'm teaching every digital twin in the world how to do this, and if there's 25 to 30 at market digital twins in the market right now, which we believe to be a fair number, then I'm teaching 25 to 30 people how to do this. And it wasn't giving us the ability to scale this up. The data layer, this is the logical place for it to come. So now we basically have integrated this into the data layer, and that can be in any environment like a Novant or a Pi. So AUROS Insights tool is a containerized tool that can do all of the analytics and integrations. We have the APIs from eQuest, Energy Plus, IES, ICD, PHPP, and Wolfie Passive into the data layers, and we have all the normalization analytics built. That's our technology. We're leveraging the technology in the industries by meeting the owners where they're at. We're bringing the data layer home, and this is home. So we do not have technology in the IDL space, nor do we want to. We don't want to compete with those guys. We want to enable and add value to those guys. Does that answer your question?
Yeah, sort of. Yeah, I'll have other questions, but we can talk.
We can meet and show this to you if you're interested, and we can show you the different digital twins that this will go into and the IDLs. The tools I'm showing you assume your client does not have an IDL and your client does not have a digital twin. If they don't have that, then we can open up a Novant for you with the user interfaces that I demonstrated for you today, because they're pretty straightforward and easy user interfaces to stand up.
What would be an example of an independent data layer? You mean a BMS system that would reference or
Nope. A
connect?
BMS system is an operational technology, and that's the box on the wall inside your building. And they do have clouds and they have their own data layer, but we cannot go to them, right? We cannot be in this space. They are going to share data out to this space. So when we show you an example of that, it would be going into a Novant system like this, where you can see, if I go back to a building that has all that integration like this one is, and I go to sources here, what you'll see is, because of the ARUs, all my BMS, BAS data is in this environment. All my lighting control is in this environment. All my security for access doors is in this environment. All my meters are in this environment. All my indoor air qualities. This is home. This is where data wants to go. And we simply said, since data's here anyways, why not bring simulation here too? That makes sense. So now we're not in a silo, and we're not trying to create another technology for your client, because your client is going to look at you like, why don't you just bring data to me? And our answer is, that's right. We should bring data to you. Data should go home. This is home.
That BACnet data must be coming out of your building automation system.
The Jasper's coming out of the Jace. That's a protocol for it. BACnet is an IP device, meaning it's on network. So when we showed you in the presentation this here,
Yeah.
converged network,
Yeah.
this is a device would go on network, that's IP, and then we would be able to discover it through our data aggregation. That's what Novant is doing. So that is a BACnet device. BACnet's IP, where Jasper is using a Niagara Jace, which is a controller that does
Yep.
that work right here. So again, from the independent data layers perspective, and you guys don't have to know this, we've done this work for you, is that we're going to be bringing in data from various sources. And if we look at those, they can be BACnet, they can be custom, which is what we did with AUROS Insights, or they can be coming from hardware controllers in the building. Again, your engineers who are doing most of your Division 25 system integration will solve for everything else. We're simply saying that we understand this, and AUROS Insights is bringing simulation into their environment in an expected way.
Okay, we'll tie up the presentation. Good information. Thanks.
Yeah, absolutely. We're happy to demo this, or any of the smart building infrastructure if you want to go deep there. The idea is, as building scientists, you guys shouldn't have to become experts in the data science world, in this chaos. You shouldn't have to become experts. If you get AUROS Insights, we're going to put you right into the right spot, which is where data wants to go. Any other questions from anyone? I'm pretty much at the conclusion of my presentation. If I go back to the PowerPoint here, I just had a set of points here for highlighting what we've talked about all along. My contact information and our book information is here. You guys will all get a copy of the deck after the conclusion of this, and the recording will be posted online. But if anyone has any other questions, I'm more than happy to take questions. All right. Thank you guys very much for your attention today. Really appreciate it.